Let's keep going with this long chapter here. So we're talking about 9i, the second derivative. Okay, the chapter so far is focused on finding the derivative, finding dy dx. Okay, and it's looked at how you do this with more difficult situations, but ultimately it has been all about finding this. We're now going to talk about using the second derivative, which can be found actually by differentiating twice. We're going to talk about using that and some new terms. Okay, so we're going to talk about concave, convex. Concave looks like a cave. Concave. Convex is the other one. Okay, that's how I would remember it. So this shape here is concave. What's actually going on is this is related to the second derivative. So we can say the second derivative, that's the same as this one here, is less than or equal to 0. It's or equal to. If it only has that, it's called strictly. Okay, but when it has that or equal to, they don't say strictly. So the second derivative is less than 0. The second derivative tells you how the gradient is changing. So the gradient is changing in a negative way. It was there, but now it's getting less positive, less positive. Well, it's negative and it's getting more negative, okay? Because it's changing in a negative way. So it gets less positive and more negative over this section. There's a special point in the middle where it stops getting more negative, but it's not quite getting positive yet. It's kind of in between both worlds. This is called a point of inflection. Point of inflection, second derivative equals 0. Please make a note of that. This is not necessarily a stationary point. It's quite confusing, second derivatives and first derivatives. Point of inflection, second derivative is equal to 0, the second derivative. It's confusing because sometimes you can have a stationary point and a point of inflection at the same time. X cubed is a very famous example of that. Okay, but it doesn't have to be that way. So point of inflection, that must mean then that the other one is convex. That's a mistake. That should be like that. If it's convex, it's negative. It's getting more positive, more positive, more positive, more positive, more positive, more positive. It's changing in a positive way. It's getting more positive. Okay, so that is when the second derivative, which can be written like this, or again, it can be written as this, is greater than or equal to 0. The questions then. The questions look quite a lot like the increasing and decreasing questions that you saw in year 1. So increasing and decreasing was all about differentiating once. These are about concave, convex, so they're about differentiating twice often. So let's have a look at some examples. So differentiate once, differentiate twice. So the second derivative, the rule to find the second derivative is this. Take your x value and multiply it by 6. So when do we have things that are concave? We have things that are concave when we talk about the second derivative being what? Being less than 0. So this part here has to be less than or equal to 0. That means on this section here, it's going to be concave. Notice this is finding a section that is concave, okay? So we differentiate it, we write the condition for concave, and then we find the values that satisfy that condition. That's quite different to this one over here. Show that it is convex for all values of x. So we're going to be differentiating twice, okay? If we want to show things for all values, have a think about where you've seen phrases like that before. You've seen them before with proofs, things like always positive and so on. So that's a clue of where to go with this question. If we differentiate twice, we get this result, 4e to the 2x plus 2. Now, convex, what's the condition for convex? The condition is that this must always be getting more positive. So that's the condition. So now we just have to justify that why that's happening. Well, look at that expression there. That expression can never be negative. Why not? Well, e to a power, this value will always be positive. Look, e to the 2x is always greater than 0. And then you're multiplying it by 4, so it's still positive. And then you're adding 2, so it's getting even more positive. So it's impossible for it to take a negative value. Okay, so that should sound a little bit familiar with things being like always positive and stuff when we did proof. It's coming in useful now. One more. So this is the curve. Find the points of inflection. So we know we need to differentiate it twice. So we're thinking 3x minus 4x minus 4, 3x squared, sorry. So 6x minus 4, something like that. And then we know that point of inflection is when it's equal to 0. So 6x minus 4 is equal to 0. That means points of inflection are when x equals 2/3. Point of inflection. So how do you find the actual point? Well, the point, it says find the coordinates. So once you have the x value, that's great. Plug it back into this initial equation because that will tell you the y if you tell it an x. So that's quite a range of different examples. It's all about understanding the condition. So concave, convex, point of inflection, second derivative, okay? Maybe even draw the cave and sort of, you can use that to work it out if you forget. Okay, it's about using that and some techniques that we've seen a little bit earlier. That will take you to 9i, I think it is in the book.